Okay, so this is part of the topic, uh, the Unit 1 kinematics in one dimension topic of frames of reference, position, displacement, and distance. This is the last problem that we're going to work on, and we're going to work through a problem here and illustrate how things are going to go for additional problems. Okay, so an ant starts at x equals 20 centimeters on a piece of graph paper and walks along the x-axis to x equals negative 20 centimeters. It then turns back around and walks to x equals negative 10 centimeters. Determine the ant's displacement and the total distance traveled. Okay, now when we start to work on problems in physics, one of the things that we don't want to do is use units that are other than meters. There'll be exceptions to this, but if I see a problem like this, I'm probably going to change my my units to meters right away. So the first thing that I do is I'm going to say x, oops, I'm going to draw here, x, let's use a pencil. I'm going to say x equals 0.20 meters instead of 20 centimeters. Remember that a centimeter is 1/100th of a meter. So if I have 20 hundredths of a meter, I would have 0.20 meters, right? And then I went to another position, and that was x equals negative. And so we're going to call this first one x0. And this next position here, we're going to call x1. And that's going to be at negative 0.20 meters. And then my next position, I'm going to be at x2 equals negative 0.10 meters. And again, make sure you understand the units here. Centimeters is hundredths of meter. Remember that cents are hundredths of a dollar, so centimeters are hundredths of a meter. And 20 hundredths of a meter would be 0.20 meters. Negative 20 hundredths of a meter would be negative 0.20 meters. And negative 10 hundredths of a meter would be negative 0.10 meters. So I've changed them into meters. So the first thing I want to do is create a frame of reference. And I know that I'm going to need some negative as well as positive. So I'm going to, and let me just move this out of the way here. I'm going to create a frame of reference. Let's make that bigger. Oh, that is as big as it gets. I'm going to create a frame of reference. I'm going to have my origin here, and I'm going to have my positive x values in that direction. I don't need to put negative x values because if I know what direction positive x is, I know what direction negative x is. So this is my frame of reference. Okay, then we're going to use labeled arrows to show all of our positions. Okay, so my first position is at this point right here, and I'm going to say that that position is shown by this arrow, and I'm going to say x0 equals 0.20 meters. Okay, so this arrow, and we'll call this a vector later on, this arrow shows that I am at a position of 0.20 meters. It doesn't say that I go from 0 to 0.2. It says that I am at 0.20 meters. Okay, I am at 0.20 meters. Okay, my second position here, x1, is down here, and I'm going to use another of these arrows to show that x1 is at negative 0.20 meters. Okay, this isn't showing that I went from 0.2 to negative 0.2. It's just showing that at my point at my second position here, I am 20 hundredths of a meter to the negative side of the origin, okay? And then I've got a third position. I'm going to use this arrow here to say x2 equals negative 0.10 meters. Okay, so these arrows are showing my positions. At the first position, I'm at 0.2 meters. At the second position, I'm at negative 0.2 meters. It's not saying anything about how I got there. It's just saying at the second point, I am here. And then this arrow is saying at the third point, I am here. And these are called position vectors because they're showing you where the position of the ant is at each of the points. Okay? Now, I'm going to write down the information that I've been given. I've been given that x0 equals 0.20 meters. I've been given that x1, the second position there, is at negative 0.20 meters. And I've been given that my third position is negative 0.10 meters. Okay, so these are my positions at each of those times, each of these points in space. Okay, I'm going to write this down too. I need the overall change of position. I want to know the ant's displacement. I want to know where it is at the end of its motion compared to where it was at the beginning of its motion. Where is it compared to the beginning of its motion? And then I also want to know the distance traveled. I also want to know the distance traveled. Okay, and remember those could be different because where I ended up compared to where I started might be different than how far I went to get there. Okay, so the next thing I want to do is figure out a formula for these things. So I'm going to write down the word formula. And remember, by displacement formula, the change in position, right, the change in x is going to be my final position. Well, which of these things is my final position? My final position is x2, right? And which of these things was my initial position? That was x0. Okay, so my final position versus my initial position. And then I'm going to come over here and write the word solve. And this is a pattern that we'll use. We'll write out our diagram, our frame of reference, and show our positions. We won't usually use the vector arrows. I'm just showing this here to show you that that's something that you could do. You could do this without the position arrows, and in fact it'll be a lot easier if we do it without the position arrows. But in this case we did. So this is our pattern. I make my drawing, then I transfer the information that I have on my drawing to a list. I state what it is that I need, and then I create a formula that's going to solve the problem that I have. I need delta x. Well, I know delta x is the final minus the initial, and so I'm just going to come over here and say delta x equals, what was x2? That was negative 0.10 meters minus my initial position was 0.20 meters. So my displacement, negative 0.1 minus 0.2, is minus 0.30 meters, right? And this is what I did. I went from here to here. That's delta x, okay? I went from here to here. That's not going to show up. I went from here to here. Okay, so that was my displacement. That doesn't take into account for the fact that I went all the way down here and then back, does it? Okay, but that's not what I'm asked. I'm asked to find out what my final position was in relationship to my initial position, and it was negative 0.3. I went negative 0.3 overall. But that's not the same thing as the distance. The distance is going to be a little bit trickier. remember we said that distances don't have direction. We don't worry about the direction. We just want the value. How many units did I go? It doesn't matter whether I went negative or positive units. I just want to know how many units I went. Okay, so for finding the distance, then I'm going to write a little formula here. D equals the distance I went in the first motion plus the distance I went in the second motion. Okay, so I went from x to x1 in the first motion, and in order to make this a positive value, again, I don't want to know what the direction is, I just want to know what the total number of units is. So I'm going to use the absolute value of that. So the absolute value, and I'm still going to say final minus initial, I want to know the absolute value of my final position minus my initial position. Okay, I want to know the absolute value of that. So this first motion here from 20 to negative 20, or 0.2 to negative 0.2, if I subtract my initial from my final, you can see that will give me a value of negative 0.4, but I just want the total units. Okay, so that's why I'm putting it in the absolute value. Then I'm going to add the motion of going from x1 to x2. So I'm going to say plus the absolute value of x2 minus x1. Okay? And these little bars, remember, mean absolute value, right? Okay, so now all I'm doing here is saying I went this many units in the first motion and I went this many units in the second motion. I'm adding these two together. And the number of units that I went is going to be the final position minus the initial position, the final position minus the initial position. So now I'm going to come over here and write this out. D equals the absolute value of negative 0.20 minus, and I'm not going to use units for that because I don't have enough space. Actually, let me move me out of the way. So I will use units. Negative 0.20 meters minus 0.20 meters. So I want the absolute value of that sum plus my final position is negative 0.10 meters. My initial position there was negative 0.20, and I want the absolute value of that. Okay, so negative 0.20 minus 0.20 is negative 0.40, but the absolute value of that is 0.40 plus negative 0.1 minus negative, that means that's a positive, right? So negative 0.1 minus 0.2 means that that's going to be positive 0.10, right? Negative 0.1 plus 0.2 is 0.1. And so that means I went a total distance of 0.50 meters. Okay, I went a total distance of 0.50 meters. Okay, so that's how we would solve that problem. I know it seems like a lot, and we'll get lots and lots of practice of this. But we've got to do this in exactly the right way, or it won't work out. Now, you could have just as easily figured out, well, I went 0.5 meters just from the diagram itself, but you need to be able to show this work. Anyway, this is the solution to this problem, and my time's about to run out of the video. Don't worry if it doesn't make sense now. We'll get lots and lots of practice, and it will make sense. I promise.